Okay, in this presentation we're going to look at statistics with OR. This is statistical modeling with OR for actuarial students. Now this follows the CS2B curriculum that actuarial students may be familiar with. Now this comprises time series analysis, probability distribution, survival analysis, and a good bit more. This particular presentation will feature time series analysis, and it's really just a way of getting familiar with a couple of the commands in OR that will be useful to you. We split it up into two parts, so there's part A and part B, and each part will have a couple of questions. So look at part A first off. The data file Expenses.csv contains records of the last 5 years' monthly expenses paid by a company starting from January 2015. So we have three questions here. Import the dataset and classify it as a time series object, specifying the relevant date. The second exercise is, assuming that the data follows yearly seasonal variations, remove the seasonality from the data using seasonal differencing. And then finally, plot a graph showing the actual data, the trend line, the trend and seasonal line, and any remaining untrended number. Plot them in the same graph and use different colors as much as possible. Okay. So first off, what we're going to do is import the expenses CSV file, which I have saved in my local directory. Okay. You should be able to access it from the website, or if you're familiar with the exams, that you might be able to find it on the actuarial exams website. So I'm going to import that as a CSV, and I just want to have a quick look at it first off. Firstly, I'm going to see what type of object it is, and if I use the class command, I find that it is a data frame. Okay, and when I get the dimensions, I get 119 rows and 1 column. That means actually that I am missing 1 month, obviously, because 119 means that I probably have 10 years. I don't have 10 years, I probably have 9 years and 11 months worth of data. So I'm missing a month from having 10 years worth of data. Okay, so the first question asks us to reclassify this or reconstruct this data set, expenses, as a time series object. What we're going to do is use this command ts just to create it as a time series, and then what we're going to do is frequency equals 12. This essentially says this is monthly data, okay, and 12 for 12 months, and it starts in 2015, month 1, okay, so January 2015, okay. So, and we're going to save that as expenses again, so we're just going to reconstruct it, and when we look at the class object, the class of this object, we get TS, time series. Okay, so we're good. So when I run it there, that's what I get, just expenses, because I want to have a look at it there, and as you can tell, I am missing 1 month there at the end, but otherwise 10 years worth of data. Okay, on a monthly basis. So before I start answering the questions, I'm going to look at this plot here, okay, and just plot the expenses just to get a look at it, just to get a sense of it. So we've actually answered the first question. This is a sort of pretty much exercise 1 completed, but I'm just getting ready now for exercise 2. There we go. The second exercise asks us, let's go back here a bit. Assuming the data shows yearly seasonal variations, remove the seasonality from the data using seasonal differencing. So what I'm going to do is decompose that data. Okay, so the command there is decompose expenses. Okay, now I'm going to assume that it is type additive. Now we'll just sort of see how that works. It does. That's the sort of default setting. So just type in type equals additive. If you get something weird looking, then try something else. But anyway, let's just go with that, what we have for the time being, just to get the hang of this first. Okay, so I'm going to call this decomposed. Okay, so this just decomposes the expenses data set, and I'm just going to have a quick plot of it there. Okay, so first off, we have 4 plots here, just sort of merged together. Observed, decomposition of the additive time series. That's what we plotted there previously. So that's just a more compact version of that, which I've just done previously. We're going to break it up into 3 parts: the trend, the seasonal component and the random component there. Okay. Ultimately, this sort of answers our question, but what we want to do really is sort of, let's see what we can do with that's a little bit, adds a little bit of value. So I'm going to take out the trend component, the seasonal component, and the random component. So these are objects that are part of the decomposed object. So I can access them using the $sign command and just taking out the component of decomposed and saving it as trend or seasonal and random accordingly. Okay, so it's just sort of break it up and take out the bits we need. Okay, so if I want to have a look at random, that's what I get. Now it goes off the page, but really it's just a data set. Okay, and I don't really need to look at it, but I just get a sense of what we're doing by looking at it there. I can plot it there also. It's good to plot these things just to sort of see what's going on. So plot random, that's what we get. You notice that the mean, it's a sort of more or less centered on the 0 line there. Okay. And that's what we sort of expect, that the error is random. Okay. So the next part is, what we have to do is create a plot where we have the raw data, the observed values, expenses, the trend, the seasonal and the trend, and the random all on the same plot. Okay, so what I'm going to do is just run that there. Now I'm just actually going to cheat a little bit because this obviously does not have the random component there, but it has all of the other components there, which is good enough for the time being. So just to sort of highlight that, what's happened is that the random component is cut off because you notice this graph, the lowest value essentially goes down to 400 to about 1200, 1200. That's the range of values there. Okay, now I'll show you how to correct for that shortly, but we'll just go along with this for the time being. Okay, so we have the expenses is the gray, okay, in the background. And in red is the trend. So let's look at the trend. We see that trend line there. Okay. We also have the seasonal and the trend in blue. And for the most part, that's sort of superimposed over the gray. Okay. So we don't really see the gray observed data because it's sort of relatively well mapped by the trend and seasonal components together. Okay. So, but it's there in the background. And finally, the random component in yellow, which actually does not come up because it's down at the bottom. So what I'm going to do is just actually break this up a little bit more. We can just look at the seasonal and trend together. Essentially, this is what we can do just to sort of get a better sense of what's going on. Sorry, there we go. What we could do here, I meant to put that in there, but what we can do if needs be is we can adjust the limits. So ylim equals 0 to 1300. Okay, and I'm going to have the seasonal and the trend component there. Okay, so you sort of see that this is the trend component in blue and the seasonal component in gray. There's multiple variations you can do of this. Okay, and also I can put in the random component. I don't really need to put in Y limits here because I'm only plotting the random component there, but that's it again. Okay, so that's good. So part B, import the time series data file ARIMA.csv and answer the following questions. So the exercises are: plot a graph for the above time series data, ARIMA.csv, plot two graphs to show the ACF and the PACF at the time series provided. That's the autocorrelation function and the partial autocorrelation function for the time series provided, and comment on the stationarity of the data based on the above graphs. Now, because of the length of this video, I'm just going to be very quick about it to show you how to do it and just what to look out for. So what I'm going to do is import my data set, ARIMA data read CSV. Okay, I have this data set here saved in memory called in my local working directory as ARIMA.csv, and I'm just going to read it in using the read CSV command, and I'm going to save it as ARIMA data. I'm going to have a quick look at it there, just to get the head of it, just to sort of quick inspection of it. Now you notice this here, 557. What's that about? That essentially means that I've created this as if 557 was the header and the name of the variable, and what happens is the R will change that to X557 because it doesn't allow column names to be start with numerals. Okay, so numeric values. So it just constructs the data set as, rather than that being the first observation, it creates that as the column name. That's what I do not want. Okay, so quick adjustment here, I'm going to add in header equals false. Okay, so that sort of says there's no header here. The first line is not the name of the columns, it's the first observation. Okay, and now you sort of see everything's right. This is my first observation, 557, and it now calls that column V1, variable 1, because there is no column name. Okay, so we're good to go. So we're just going to check the class of it there. So class ARIMA data frame, and the dimensions, it's 100 rows and one single column. Now, we're not actually given any information in the question about, is it monthly data, or is it frequency data, or monthly or weekly or anything like that. So essentially what we're going to do is just leave it as is. We're not going to construct it as a time series object like we've done previously, because we don't really know how it's constructed, so we'll just leave it as the raw data. What I can do, just to plot the data first off, ARIMA data is the name of the data set. Put in the title here, main equals time series data, and on the y-axis put in the label data, and I'm going to plot that using ts.plot. That's a time series plot. Okay, so that gives us our time series. So the next question is asks for the ACF and the PACF. So very similar to what we've just done previously. Rather than time series plot, ts.plot, we just write in ACF. Okay, and you notice that most of these little lines coming out of that zero line, none of them go outside the blue bands that much. Just the first one, but after that they stay more or less not noticeably transversing those blue bands. Okay, so we'll just talk about that shortly, but that's what we noticed, that this point here, you know, that the first line is, you know, 1, goes up to 1, but afterwards it just mostly within those blue bands. That's what we really notice. Likewise, the PACF is this partial autocorrelation function, and you notice that the lines more or less stay within the blue bands. Now they can stick out a little bit, but that's not really worrying. Okay, so the ACF drops to 0 relatively quickly, denoting that the series is stationary. Okay, essentially just go back here to ACF, that apart from the first line coming out of this, the first observation, that they're all close to 0. That's just essentially rounding error. Now what we're reading there is a sort of statement or a sort of indication about the stationarity of the plot of the data, and that sort of says it's fairly stationary based on the ACF. Okay, we'll leave it there.